So now we'll take a look at how we can do this analysis with OpenDSS. And I'll be talking about this also during some of the online class sessions, because I know this can seem kind of complicated, which is why I've given you all these different examples. And what we did initially in the OpenDSS lecture is we focused on doing snapshot analysis, and that would be kind of comparable to what we're already doing in tools like Windmill, is we're just running the case for one given point in time. But now what we want to take a look at is how we can extend this for time series analysis. And once we have this time series model, and there's a lot of different things we can look at, we could kind of look at what's going on with losses over the course of a year. We could see, like, say, if we're going to put in distributed generation, what's going to be the impact on losses. We could look at rapid voltage fluctuations in terms of seconds or minutes. And we could also take a look at the steady state over voltages, which is that plus and minus 5% we've talked about before. So we'll use the same circuit as we did for the Windmill cases, but we're going to choose a different location this time. We're going to choose the J5 location. We're going to look at a larger plant size. And this will just kind of exacerbate or make worse the issues that we saw before for the 2 megawatt plant that was closer to the substation. And so this is kind of a ways out, but it's still on the backbone of the circuit. And this would be kind of typically the sort of things you look at, like an interconnection or system impact study. So when we do this analysis, we usually begin with a base case without the PV, because what we're really wanting to look at is what's going to be the negative impact over and above where we're at right now. If you jumped right to the PV case, maybe there's already voltage problems, and so the PV is not really making it worse. It already kind of existed. And if you haven't run quasi-static analysis for the circuit yet, you always have to be running some no PV base case. And then you add the PV and you can see what the impact of just the PV would be. So when we're doing the study, what we need to do is we need to set up a time series run. And typically we're going to run this in daily mode, but you could run it in yearly mode as well. In this case, I'm going to run this at a 1 minute time interval. And I mean, the shorter the time interval, the more accuracy you would have. But if we ran this at 1 second intervals, that would be a lot of data. And so 1 minute seems to be an interval that utilities could conceivably get their SCADA data into a form that you could use for a study. Then we're going to model this PV system in OpenDSS. So I have to create the additional files for that over and above what a Windmill export would give. And then once we have the study running, and then we could retrieve the results. And then the things we're going to be looking at are going to be things like, what's going on with the top of the feeder power flow, to what degree do we get reverse power flow. We can look at maximum minimum voltages on the feeder, like those steady state values, and see if we stay within the plus or minus 5%. We could look and see what the impact is going to have on the line regulator, as far as its ability of being able to regulate voltage, and if we'll get additional tap changes or not. And then we sort of focus on voltage at the point of interconnection, because this is usually a worst case voltage in this situation if we're looking at rapid voltage fluctuations. So this shows the elements in a master file for OpenDSS, and we talked about this when we went through the basics of OpenDSS in the lecture in the previous week. And you'll see a lot of these same files in here that we had before for doing snapshot analysis. What has to be added now would be, we need to have a load shape file, because this is going to give us the time of day characteristic. We obviously need a PV file, so modeling the PV system. And then if I have some additional monitoring in here, I might have a monitors DSS file. And if putting in energy meters, this is a more sophisticated type of meter, then I'm also going to be putting the energy meter into usually its own file as well. And so as far as some additional settings you're going to have, you're going to be setting this up for demand interval analysis, and we could create a case name. This is just something that's going to be used to name the files. We're setting the demand interval to true. Demand interval verbose functionality is turned on. And then the mode I'm going to run this on in daily mode. We didn't need to have the mode before when we were getting into the snapshots, because by default it does a snapshot. But now if we're going to run this in daily mode, we need to explicitly set this with the step size and the number of points that we're going to include. So if you have minute resolution, you have 60 minutes in an hour, you multiply by 24 hours a day, that gives you the number of points. So this is the same as before. We have our voltage bases. We run calculate V to set our voltage bases up within OpenDSS. And then we would actually then solve the power flow. Something else we would also want to do is, if we have results, we may want to export those to Excel type CSV files. And so we could export things to CSV. You would have an export monitors DSS file for exporting the various monitors. But then something else you would also have when you run these studies as well is you have what's called an event log and a capacity check. And so the event log would have things like if a control operation occurred, it would track that. Like if you had a tap change or capacitor switching, it would track that. And then you could also export capacity information about whether we're getting overloads or not. And then you can also use built-in OpenDSS plotting. I think this would be more for your own use to kind of see the results rather quickly. They're not the neatest looking plots. And so if I were doing a professional study report, I probably wouldn't insert these types of plots. I would probably export to Excel, use Excel plotting for that. But if you just want a really quick output, then you can use these built-in plots that OpenDSS provides. So let's talk about how to set this up. First thing we need to do is we need to define a load shape, and we need to modify our load file. And so what the load shape is basically multipliers, usually between 0 and 1, where if I have peak values of load already defined for all my loads, then this is a multiplier I'm going to apply to both P and Q. And so this shows, for different time steps, these shows these multipliers. And so you'd have a P multiplier and you have a Q multiplier. In this case, this is just kind of showing the load shape during the day. It's not a huge deviation that I'm showing right here, because I'm only showing this for like the first few points. I'm not showing it like for the whole day. Then what you would need to do is you need to define a load shape command within OpenDSS. And so this is going to go into a load shape.dss file. And what it's going to do, it's going to link to where I've got these points at. So these points are in a CSV file. And so what I'm going to do is I'm going to create a new load shape. I could call that load shape 24 hour. Number of points is 1440. And the interval is in 1 minute per point. And then I'm going to get the P multiplier and the Q multiplier values from the CSV file called load shape _ 1 minute. All right. So this is in column 1, this is in column 2. The other thing I need to do is this original load file was set up for just modeling snapshot, just for the peak load. So what I have to do is I have to add an additional column in here, because these are the original peak values. I had an original entry in here called daily equal load shape 24 hours. And I have to add that to each load. And so what you do is you open up the file and you can do a global replace, where I replace the last part of this by this tilde daily equal to load shape 24 hour. And then that sets this up where the loads are going to be modeled in this quasi-static format. The other thing, again, you have to make sure of is you have the correct dynamic mode set. So again, it defaults to snap, but you can run a daily, you can run a yearly. The default for daily, if you don't see anything, is going to run this in 1 hour increments. And what's going to happen is when you run a daily study, then any monitors you've got set get reset at the very beginning. So remember that OpenDSS is an engine. It basically stores all the circuit information. But if you run this again, then what it'll do is it'll reset the monitors. So again, if we were going to use, like, say another interval like 15 minutes, then you'd have 96 of those during the day, right? And then the step size in that case would be 3,600 divided by 4. We're going to have like 900 seconds per point. So anyway, you could use different step sizes depending on what data you have. And if you're talking about SCADA data, they usually would at least have this on an hourly basis, but then depending on what you're trying to get out of the study, you may want to break this into 15 minutes or 5 minutes or 1 minute. A second, that's a lot. That's a large data set. Usually if I would be trying to do this quasi-static analysis, I'd probably be shooting for like a minute. The other thing you need to do is you need to start modeling your PV system in OpenDSS. And what you would do is you would set up a PV-DSS file. And then what you would set in here is you would set in the size of the array. And this is usually based on the assumption that you're going to get from your panels 1 kilowatt per, you're going to get 1 kilowatt if you have like a square meter of array. And so basically what you do in this case is you're not inputting power indirectly. What you're inputting in this case is irradiance. Irradiance would be a number between 0 and 1. And so if you're like at 0.8, that means you're going to be 0.8 at the rating of the panel, let's say, right? And so what we do in this case is we would put in the kVA value. It's going to be 3,000. We're setting this up. We're going to set this up for the default assumption. And then what we're going to be doing in this case is we're going to make sure our maximum power output matches. And then we're going to set daily equal to irradiance. And what that's going to do is that's going to suck data in corresponding to our load shape for irradiance. And so even though this is generation, we still use the load shape functionality. It's still a curve that we're going to get from a spreadsheet. And we're going to say new load shape, and we're going to call that load shape irradiance. And it's going to have 288 points because this is going to correspond to a time interval of 5 minutes. And the CSV file this is going to be located in is going to be a file called irradiance_5 minutes.csv. Note that you can have a different time interval for your PV data if that's needed. It'd be nice to get this in 1 minute increments, but suppose it's at a different increment. What OpenDSS will do is it'll interpolate between the points. And so if you have a value here at one time instant and a value another instance, and if you're doing your circuit study at 1 minute, then basically what OpenDSS does is it can do like a linear interpolation between the points. The other thing you need to do is you need to set up your monitors. And so again, monitors are places where you're going to be taking measurements. And so you're going to set up a monitor called PV Monitor VI. This is for monitoring voltage and current. You would set up another monitor called PV Monitor PQ. And note you have a mode here. Mode 0 means that you're going to monitor voltage and current. Mode 1 means you're going to monitor power. And so the element is going to be pvsystem.pv site in this particular case right here, because this was the name of the, we use PV site as the name of the PV system. So we just have to be consistent when we set up the monitor. And note this is going to be at terminal 1. That's basically going to be the default terminal in this case. Where this gets a little bit confusing sometimes is when you're using line elements that have terminals 1 and 2, so you have to make sure you use the right one. But just set something up kind of similar to this in your project. All right, so when we've done this, then what we're going to have in our, what we're going to have is we're going to have an irradiance curve. This is going to be purposely a radiance curve for a cloudy day because we want to look at the impact of cloud cover. And so you can see there's a lot of deviations in this output right here. And basically what we're going to be assuming that the irradiance maps directly to a real power output for this array. So then if you look at the irradiance and if you look at the real power output, you see there's kind of like a 1-to-1 correspondence between the two. And there's different sites where you can get this sort of data, like National Renewable Lab has a data set, you know, where you can actually pull this information for different locations in the United States. All right, so once you've got the load shape file set up and you got your PV set up, then what you could do is you can run your analysis. And again, you know, you got these various monitors that you're setting up. You got the monitors right here for the PV. Again, these monitors all run in different modes. And so if you have mode 0, then you would be monitoring voltage and current. If you have mode 1, that's power. Node 2 would be like a tap position for like a regulator. And then what mode 3 is used for, if you have like a battery, you can use that for looking at things like battery state of charge. So in this case, what we're doing is we're defining these monitors. And what we're going to do is we're going to set this up again for looking at power. The other thing you could do on here too is you could put these in polar coordinates or rectangular coordinates. And so in this case right here, I'm going to say I don't want this in polar. You know, I have that feature set equal to no in this case. And then if I wanted to look at a monitor for my tap changes, this is for the downstream device right here, then I could set up a monitor for that where the element is going to be transformer regulator 168, which is that downstream line regulator. I put that at terminal 2 because, you know, as far as the regulator model, the source side is terminal 1, the load side is terminal 2. So I want to make sure I have that. I'm setting this up to look at my tap positions. And we could talk about this later on if you guys got questions once you start working on your projects. But this is the thing that kind of gets confusing about OpenDSS is getting the values out of it, right? And kind of knowing, you know, what sort of monitor commands to put in and things like that. The other thing is that if you want this dumped to a CSV file or to a plot file, the fact you set up a monitor doesn't mean you see it. That just means that OpenDSS is capturing it. And so what you need to do is you need to export, if you want to put this into a CSV file, you need to export the monitor. And so you'll put this information in an export monitors DSS file, and you'll have commands in there like export monitor, and you'll give it the name of the monitor, and then it just simply dumps all that stuff in the spreadsheet. And again, if I were going to do a professional report, I would really suggest that you dump this into a spreadsheet and do your own nice looking plots instead of using the plot command in OpenDSS and kind of coming up with these plots that just aren't as good looking, right? Again, that's okay if you're just kind of running studies for your own purposes, but if you're going to do professional looking reports, you ought to, dump it to a CSV file and then use the plot capabilities in Excel. What the energy meter does is this is something you could actually use for tracking what's going on like in a certain zone of the system. In this case, we'll just have a zone for the whole system. And it doesn't only just look at power or say like energy, but it could also look at things like losses. It actually tracks for the time duration of the study, like the maximum and minimum and average values of voltage. And so this is kind of used where you need to find out, like what are best case or worst case values, and instead of having to go through all the detail for each node, it just simply says in the zone, this was a high voltage and this was a low voltage. So you got to make sure that you have set demand equal to true. And then what this basically would give you the ability of doing then is then dumping these results into another CSV file. And so, in this case right here, what we're doing is we're setting up a new energy meter. This is going to be monitoring the top of the feeder. So this is going to be the line I have called OHB1. This is the feeder at the top of the circuit. I'm going to do this from the from terminal. And then this is going to be I'm going to want a phase voltage report. And again, once you start using OpenDSS and you read the documentations, this will be a little clearer. But again, you have to put a lot more effort into finding your output results. It doesn't automatically just print out a bunch of reports like Windmill does. You actually got to go and tell specifically OpenDSS what it needs to give you as far as results. So anyway, as far as retrieving results in here, when we run this master.dss file, you'll note that we got this case name generated. What it's going to do is going to dump out a bunch of files that make use of your case name, whatever you gave it. You're going to have this system meter file that's going to be included. It's going to have KWH and peak KW and total losses and peak losses and stuff like that in there. Again, it's going to gear in on peak day or whatever name you give it in here. And what this does is it's going to kind of coordinate with the energy meter in a way. So anyway, we'll dig into this a little bit on some of the online classes, because it's just kind of hard for me to explain unless I can actually run it and then show you the files like a little bit more expanded demo on this. But when we look at some of these CSV files, like when we export like the event log, this kind of shows an example right here of an event log. So basically when the controller operated, where it would change the taps, for example, that would show up as an entry like an event log. So anytime the control activated, like it switched the capacitor on and off, it would set up an entry in the event log. So you got to make sure you export that. And then the other report we have is export capacity, where it'll see where we are with respect to our capacity constraints. All right. So finally, when you look at the results, and these are plots that are made in Excel. All right, these aren't plots that are made in OpenDSS. But if we're comparing our base case to our case with PV, what you would see initially for your base case is what we're showing here in blue. This is what we're looking at as P and Q at the top of the feeder. Now, PV is not going to impact Q any because that was set up as a constant power source. However, it is going to impact what we see in terms of real power flow. And basically what PV is looking like, it's looking like negative load. And so what we expect to see at the top of the feeder is less real power, right? The fact is, though, that we have an intermittent output. And so when we hit the cloud cover, what happens is we lose the PV. And basically this line we have in orange is with the PV, what happens is reverts back to our load value. But what this is going to cause, what the PV is going to cause, is a negative load effect, where basically it's going to kind of cause the power flow at the top of the feeder to kind of droop down. In real systems, we actually see cases where we can have so much PV that the flow actually goes negative. And so the issue we run into, if that flow really goes negative and then the PV goes away, then that consumption swings back to positive again. And this is where we run into a lot of issues with regulator control and maybe protection, things like that. If we take a look at our line regulator voltage, on the left shows the base case without PV. And we could see that because of increases in load, we run into situations where we need to have the taps operate. And so you could see during the day that you have these changes in tap position, which is going to cause kind of abrupt changes in the voltage. And this happens because of load deviation. So when load deviates, the line regulator reacts, and we basically are going to see this voltage kind of swinging around a little bit. And the scales are set up where this kind of looks like a lot of voltage fluctuation, but it's really just the regulator doing its normal thing and trying to keep the voltage within the bandwidth. Recall again that we have a bandwidth that this regulator is working between. So unless the changes go outside the bandwidth, the regulator is not going to do anything. So this is kind of what you're seeing in this case, is the voltage going outside the bandwidth and the regulator kicking in and kind of pulling it back in within the bandwidth range. What the PV does is it does a couple things. It gives you a few more tap changes, and the other thing you see is we see a lot more voltage deviation. And so when we talk about voltage flicker, rapid voltage change, this is one thing we have to look at is, first of all, does it put more tap change wear and tear on the regulator? And then second, does it cause a lot of rapid voltage change that the regulator can't react to? And this kind of shows some of these tap changes. You know, this is the position of the tap, and you can actually get this in the reports from OpenDSS, where you could see for the base case we would have in blue, and for the PV case this is shown in orange. And it may not look like that many more changes, but we just kind of looked at a very narrow time span right here. And so what you would be worried about, it'd be what would be the percent increase of tap changes over the base case, and you'd figure out like how much extra wear and tear is this going to put on your regulators, because regulators can only operate for so many tap changes before they have to be maintained or maybe replaced. This shows the voltage at node J5. So this was at the interconnect point. And you can see you get these normal swings in voltage, and this is showing this for phases A, B, and C. What the PV does is it causes a shift upwards in the voltage. So you get the voltage rise to the PV, but because of the intermittency, what happens is the voltages look very ragged. And so again, you'd be worried about not only is this going to go above 1.05 in steady state, but to what degree are we going to have rapid voltage change that might exceed our percent limit. And then this shows power at node J5. And this is probably isn't something we're as concerned about. We're more concerned about what this is going to look like at the top of the feeder. But again, this kind of shows you the impact of the intermittency. Okay, so anyway, what we'll do in this last segment is we'll take a look at some mitigation methods and how we model that in OpenDSS.